The universe is filled with mysteries. Some of them are bright and loud, flashing across the sky in a supernova or whirling in the heart of a galaxy. But others are quiet, hidden behind veils of cosmic dust, completely invisible to the human eye. Just beyond the range of visible light lies an entire unseen universe, a realm where more than 1.5 billion stars, galaxies, and ancient stellar relics wait patiently in the dark. It is as though a curtain has been drawn across our own galaxy, preventing us from truly seeing where we live. For centuries, astronomers have stared up at the sky and tried to imagine what might lie beyond those thick curtains of interstellar dust. Traditional telescopes, limited to visible wavelengths, show us only a small fraction of what is actually out there. And yet, the secrets hidden in that darkness may hold answers to the biggest questions we have about our galaxy, its history, its structure, and even its future. But now, thanks to advances in infrared astronomy, we finally have a way to look through that fog. And what we are starting to see is astonishing. This is the story of how astronomers lifted the veil. Using a powerful instrument called VISTA, the Visible and Infrared Survey Telescope for Astronomy, they created the most detailed three-dimensional infrared map of the Milky Way that humanity has ever seen. It is a breakthrough that lets us peer into the very heart of our galaxy, revealing stars that were once invisible, star clusters long buried in dust, and structures that challenge our assumptions. Join me on this journey as we discover a galaxy we thought we knew, and the hidden universe it contains. High in the Chilean Andes, under one of the clearest skies on Earth, stands a remarkable machine. Its name is VISTA, short for the Visible and Infrared Survey Telescope for Astronomy. Operated by the European Southern Observatory, VISTA is not just another telescope. It is a window into the invisible. Built to scan the sky in infrared light, it allows us to see deep into regions that are completely opaque in visible wavelengths. Dust clouds that once blocked our view now become transparent under its watchful gaze. VISTA began its mission in the year 2010, and over the course of 13 years, it observed the sky on 140 nights, collecting data that had never been possible before. By the time the project wrapped up in 2023, VISTA had taken around 200,000 images and gathered over 500 terabytes of data. That is the equivalent of streaming ultra-high-definition video continuously for nearly 3 years. Its camera, known as VIRCam, is specifically designed to detect infrared wavelengths between 900 and 1,200 nanometers, far beyond the range of human vision. What makes infrared so powerful in astronomy is its ability to pierce through dust. Visible light, which ranges from about 380 to 700 nanometers, is easily scattered or absorbed by dust particles floating in space. That is why the center of our galaxy, despite being packed with stars, appears so dim and patchy in traditional images. But infrared light behaves differently. It glides through the dust, carrying with it the glow of stars and structures we would otherwise never know existed. Unlike optical telescopes, which show us a universe that feels sharp and familiar, VISTA reveals a galaxy that is raw, tangled, and unexpectedly rich. It shows us failed stars called brown dwarfs that emit almost no visible light at all. It shows us hidden star nurseries where new stars are being born behind thick clouds. And it shows us the distant reaches of the Milky Way, where ancient clusters of stars orbit quietly in the shadows. VISTA does not just take beautiful pictures, it rewrites our map of the galaxy. The VISTA Infrared Survey is more than a technical accomplishment. It is a profound change in how we explore the universe. By combining wide field coverage with deep, high-resolution imaging, it gives us not only a flat snapshot, but a layered, three-dimensional view of our galaxy's structure. For the first time in history, we can trace the full span of the Milky Way's luminous mass, across dust, through gas, and deep into the galactic center. In doing so, VISTA transforms what was once a blurry silhouette into a clear, complex, and breathtaking portrait of our cosmic home. Imagine standing in the middle of a forest at night, surrounded by trees, but unable to see more than a few feet ahead. That is what it has been like trying to map our galaxy from within. For centuries, astronomers have looked outward, at other galaxies, nebulae, and distant stars. But the structure of our own Milky Way has remained largely mysterious. We knew we were inside a spiral galaxy, but the exact shape, the number of spiral arms, and even the total number of stars were all questions still open for debate. Thanks to the VISTA telescope and its groundbreaking survey, that mystery is finally starting to lift. Between the years 2010 and 2023, astronomers embarked on a mission to build the most detailed infrared survey of the Milky Way ever attempted. This massive effort was known as the VVV project, short for VISTA variables in the Via Lactea, using the Latin name for the Milky Way. It was later expanded into the VVVX, or the VVV Extended Survey, which allowed the team to push even deeper into the heart of the galaxy. The data collected from these surveys is extraordinary. With around 200,000 individual images and over 500 terabytes of information, the team has built the most complete infrared catalog ever made of the Milky Way's central regions. To put that in perspective, the survey covered an area of the sky equivalent to over 8,000 full moons. Within that space, astronomers detected more than 1.5 billion stars, clusters, and galactic structures, many of which were completely unknown before. But this survey is not just about quantity. It is about depth, clarity, and dimension. Previous attempts to map the Milky Way in visible light struggled to see through the dense clouds of gas and dust that permeate our galaxy. The result was often patchy and incomplete. But with VISTA's infrared capabilities, astronomers could finally trace the full structure of the Milky Way, including the long-obscured regions near the galactic center. The result is a three-dimensional map that shows not only where stars are, but how they are distributed in depth and time. One of the most striking outcomes of this effort is the clarity with which we can now see the galactic bulge, the dense, bright central hub of the Milky Way. This region was once thought to be almost entirely inaccessible, hidden behind thick curtains of interstellar dust. But now, with the veil lifted, we can observe its structure in astonishing detail. We can trace the bulge's size, shape, and stellar composition, and begin to understand how it connects to the spiral arms that wrap outward in the galactic disk. The VVV and VVVVX surveys have also revealed the presence of intricate stellar streams, new star clusters, and variable stars that help serve as cosmic markers. These discoveries allow astronomers to better understand the gravitational architecture of our galaxy. By plotting the movement and brightness of stars across the map, scientists can begin to reconstruct the history of star formation in the Milky Way, and even glimpse how it may evolve in the future. It is as if we are not only drawing a picture of our galaxy, but watching its story unfold. What makes this map even more powerful is its synergy with data from other missions. For example, while VISTA operates in the infrared, the Gaia mission from the European Space Agency focuses on visible light and precise star positions. When combined, these two datasets create a multi-dimensional view of the galaxy unlike anything seen before. Infrared reveals the hidden stars, Gaia reveals their exact positions, motions, and distances. Together, they form a cosmic lattice, a skeleton and skin of the Milky Way's living body. The creation of this three-dimensional map is not just a scientific triumph, it is a philosophical one too. For the first time, we are seeing our own galactic home not as a guess, or a model, or a simulation, but as a real, measured, observable structure. We now know where we are within that structure, how far we are from the center, and what lies in every direction around us. It is a reminder that even though we live inside the galaxy, we are finally starting to see it as a whole. And in doing so, we are beginning to understand not just the Milky Way, but our place within it. At first glance, the Trifid Nebula is already a stunning sight. Located about 9,000 light-years from Earth, it is a star-forming region glowing softly in visible light. The name Trifid comes from the way dark dust lanes appear to divide the nebula into three distinct lobes. When observed in visible wavelengths, we see a cloud of gas bathed in pink from ionized hydrogen, with a faint blue haze scattered by hot, young stars in the foreground. It is a beautiful and mysterious image, but it only tells half the story. What you do not see in visible light is what lies behind that glowing cloud. Much of the light from the stars inside and beyond the nebula is blocked by dense clouds of dust. To the naked eye, or through a standard optical telescope, the Trifid Nebula seems like the end of the line, a luminous curtain with little beyond. But in reality, it is just the surface layer. The true depth and complexity of this region can only be revealed in infrared light, and that is where the VISTA telescope comes in. Using its powerful infrared camera, VISTA observed the Trifid Nebula in a whole new way. The result is breathtaking. Where once there was only glowing gas and shadowed dust, the image now reveals a dense background of stars, hundreds of thousands of them, previously hidden from view. The dust, which was opaque to visible light, becomes almost transparent in infrared wavelengths. What was once a foggy wall becomes a window, letting us see through the nebula into the far reaches of the galaxy. Among the stars revealed are two particularly interesting ones, Cepheid variable stars, identified for the first time in this region. While they appear to be close to the edge of the nebula in the image, these stars are actually located far behind it, possibly 7 times more distant. Cepheid variables are incredibly important in astronomy because their pulsations follow a predictable pattern. By measuring the period of their brightness, we can determine their absolute luminosity, and by comparing it to their apparent brightness, we can calculate their distance. In this sense, these stars act like cosmic rulers. By placing them at such great distances, we can start to build a more accurate three-dimensional picture of our galaxy. Finding even a handful of these stars behind a dusty nebula is remarkable. But what is even more fascinating is how they challenge our assumptions. For a long time, it was believed that the far side of the galaxy was simply out of reach. Too far, too faint, too obscured. But now, thanks to VISTA's ability to see through the dust, we are discovering entire layers of the galaxy we barely knew existed. The comparison between the visible and infrared views of the Trifid Nebula is more than a visual contrast. It is a revelation. It shows us how limited our understanding has been when using only one window of the electromagnetic spectrum. It also reminds us that beauty and wonder often lie just beneath the surface, waiting to be uncovered by the right kind of light. As we look at the night sky with new instruments and deeper wavelengths, we are not just observing stars. We are uncovering the hidden structure of our galaxy, piece by piece, one glowing nebula at a time. In the search for understanding our galaxy, one of the most powerful tools astronomers rely on is not a machine, but a type of star. Cepheid variable stars are pulsing beacons scattered throughout the Milky Way, and they have changed the way we measure the cosmos. These stars brighten and dim in a regular rhythm, each cycle lasting days or weeks, depending on the star's mass. This consistent behavior allows scientists to calculate how intrinsically bright a Cepheid star truly is, and from there, determine how far away it must be. The principle is simple, but profound. If you know how bright something is supposed to be, and you measure how bright it appears from Earth, then you can calculate the distance between the two. That is why Cepheid stars are often referred to as standard candles. They are one of the few objects in the universe that allow us to directly measure cosmic distances with a level of accuracy that can span tens of millions of light years. Without them, our galaxy would be more like a painting, flat and beautiful, but lacking true depth. In the infrared survey conducted by VISTA, astronomers identified dozens of Cepheid variables, many in places where no one expected them to be. Most astonishing was the discovery of 35 young classical Cepheids right in the galactic bulge. That central region of the Milky Way, once thought to be populated only by old stars, was hiding a new generation. Based on their pulsation periods, some of these stars may be as young as 25 million years old, remarkably young compared to the galactic average. Finding young stars in the heart of the galaxy was a surprise in itself. But what these 35 Cepheids revealed went even further. When plotted on a map, they traced a narrow structure running straight through the bulge, a thin, flat disk of young stars buried behind gas and dust. This structure had never been seen before. It had remained invisible in previous surveys, hidden by the limits of visible light and the thick material that cloaks the galactic center. VISTA's infrared vision brought it to light. The implications are far-reaching. This thin disk suggests that the process of star formation has been quietly unfolding in the midplane of the Milky Way for the past 100 million years, and it forces scientists to reconsider long-held beliefs about the bulge being exclusively ancient. Perhaps this region is not a relic frozen in time, but a dynamic zone of ongoing evolution. Perhaps new stars have been forming all along, hidden beneath layers of obscuring dust, their light finally reaching us thanks to the right kind of telescope. Cepheid variables have long been guides in our journey through space, but this new discovery shows they are also guides through time. By revealing where young stars are, they help us piece together when and how those stars were born. They are markers not just of distance, but of stellar history. And as more of them are found, especially in hard-to-see places like the galactic bulge, they will continue to redefine our understanding of what kind of galaxy we live in, and how much more remains to be discovered within it. For a long time, the central bulge of the Milky Way was thought to be an ancient place, a crowded, spherical concentration of old stars that had formed early in the galaxy's history. This idea had gone unchallenged for decades. It made sense. The bulge was dim in visible light, full of red, low-mass stars, and largely inactive in terms of star formation. In the minds of many astronomers, the bulge was like an archaeological site, something to study for its past, not for its present. But recent discoveries have flipped that idea on its head. When astronomers use the VISTA telescope to conduct the VVV infrared survey, they expected to confirm this traditional view. But instead, they found something extraordinary. Buried beneath the dust and gas of the galactic center was not just a scattering of young stars, but a structured, organized feature. a thin, flat disk of youthful stars running right through the bulge. It had been completely invisible in previous surveys. Only by using infrared light could scientists detect its presence and begin to trace its extent. The discovery came through the mapping of classical Cepheid variable stars, those pulsating markers of distance and age. The 35 Cepheids found in the bulge region were not randomly scattered. When their positions were plotted, they revealed a thin, elongated shape, aligned with the plane of the galaxy. This disk of stars, young by galactic standards, had somehow managed to survive and thrive in a region previously assumed to be dominated by old stellar populations. Its very existence was unexpected. These stars are estimated to be less than 100 million years old. To put that into perspective, our own Sun is more than 4 billion years old. The youngest of the Cepheids identified in the disk may have formed as recently as 25 million years ago, a blink in cosmic time. The fact that such youthful stars exist in the center of the galaxy suggests that the bulge is not a quiet relic, but a dynamic environment where new stars are still being born. Star formation, it seems, did not stop billions of years ago. It never stopped at all. This discovery challenges the long-standing models of galactic formation. Many believe that the bulge formed early through violent mergers of smaller galaxies, producing a dense population of old stars. Others propose that it grew slowly as gas funneled inward, triggering new star birth over time. The existence of a young stellar disk supports the latter theory. It implies that the bulge may have continued to evolve as part of the larger galactic structure. Rather than being separate, the bulge and the disk might be linked by a shared, ongoing history of star formation. The implications are profound. If the Milky Way can quietly sustain star formation in its core, then perhaps other galaxies can as well. Perhaps galactic centers are not just crowded graveyards of ancient stars, but regions of renewal and rebirth. The young disk within the bulge, hidden for so long, is not just a surprising feature. It is a clue, a thread in the tapestry of how galaxies grow, change, and sustain themselves over billions of years. And now that we have seen it, we must rethink what we thought we knew about the very heart of our galactic home. While young stars like the classical Cepheids offer a glimpse into the present and near future of our galaxy, there is another kind of star that looks much farther back. RR Lyrae stars are among the oldest known stellar populations. Unlike the younger, more massive Cepheids, RR Lyrae stars are small, ancient, and incredibly stable in their rhythmic pulsations. Each one of these stars is a time capsule, formed more than 10 billion years ago, and they carry with them the memory of a much earlier Milky Way, a time when the galaxy was still taking shape. Traditionally, RR Lyrae stars are found in globular clusters, which are massive, tightly bound groups of tens of thousands to millions of stars. These clusters orbit the outskirts of the galaxy and are some of the most ancient structures in the known universe. Finding RR Lyrae stars is often a sign that an old globular cluster is nearby, or once existed in that region. So, when astronomers discovered 12 RR Lyrae stars right in the heart of the Milky Way during the VISTA survey, it was more than surprising. It was historic. For decades, astronomers believed that globular clusters did not survive near the galactic center. The gravitational chaos, the radiation, the density of stars, it was all thought to be too extreme. Any clusters that might have wandered too close would have been torn apart long ago. But the presence of RR Lyrae stars near the core tells a different story. These stars may be the fossil remains of a long-lost globular cluster, one that was pulled apart and dispersed, but whose stellar remnants still glow with quiet persistence. This discovery adds a vital piece to the puzzle of how the central bulge of our galaxy formed. One major theory suggests that bulges in spiral galaxies were created during violent collisions, when smaller galaxies merged, bringing with them their own stars and clusters. Another theory proposes a gentler process, where gas slowly sank toward the center and formed stars over billions of years. The identification of ancient RR Lyrae stars in the galactic core seems to support the idea of early mergers, because these stars likely arrived there as part of one or more ancient globular systems. It is worth noting how challenging this discovery was. In the central regions of the Milky Way, RR Lyrae stars are extremely difficult to detect. They are not very bright, and they are often drowned out by the glow of younger, hotter stars and obscured by thick clouds of dust. Without infrared capability, they would have remained hidden indefinitely. But thanks to VISTA's survey power and ability to monitor the subtle brightness variations over time, these ancient markers could be identified and tracked with precision. The 12 RR Lyrae stars at the galactic center are more than just points of light. They are relics, evidence that even in the most crowded, chaotic parts of the galaxy, the past is still present. They hint at ancient collisions and long-gone clusters. They whisper of an earlier time when the Milky Way was still assembling itself, one cluster at a time. And perhaps most importantly, they remind us that hidden within the heart of every galaxy are clues not only to what it is, but to what it once was. Globular clusters are among the oldest and most mysterious structures in the galaxy. These dense, spherical collections of stars, each containing tens of thousands to millions of members, are held together by gravity and orbit the Milky Way like ancient satellites. For decades, astronomers believed they had found and cataloged most of these clusters. After all, globular clusters are large and luminous. But that assumption was based entirely on what we could see in visible light. As it turns out, some of the most intriguing clusters were hiding in plain sight, obscured by cosmic dust. In the year 2011, the VISTA infrared survey revealed something astonishing. when astronomers pointed their instruments toward a region containing a faint red splotch known as UKS1, a previously known globular cluster, they noticed something odd. A second, much dimmer concentration of stars appeared nearby, invisible in visible light, but suddenly clear in the infrared. This new object would come to be known as VVVCL001, and not long after, another hidden cluster, VVVCL002, was discovered in the same region. These two new globular clusters are special for several reasons. First, they are remarkably faint. Had it not been for VISTA's infrared sensitivity, they would have remained completely undetected. Second, their proximity to UKS1 raised an exciting possibility. Could they be gravitationally bound? If so, this would make them the first known binary globular cluster pair in the Milky Way. Binary globular clusters have been observed in other galaxies, such as the Large Magellanic Cloud and Centaurus A, but never in our own. The idea of a binary globular system is both rare and scientifically valuable. If two globular clusters are gravitationally interacting, they might eventually collide and merge, forming a supermassive cluster. This process could help explain the existence of unusually massive globular systems like Omega Centauri. Studying a candidate binary system so close to the center of the Milky Way offers an unprecedented opportunity to witness this kind of dynamic interaction in our own galactic backyard. Though it remains unconfirmed whether VVCL001 and UKS1 are truly bound, the possibility alone has stirred great interest. But the story does not end there. The discovery of these clusters opened the door to a wider hunt. As astronomers expanded the VISTA survey and analyzed deeper layers of the infrared data, they began finding more of these hidden relics. Dozens of faint and previously unknown globular clusters have since been identified near the bulge and disk, regions that were once thought too dense or dusty to allow proper observation. Each new discovery adds weight to the idea that our catalog of globular clusters was far from complete. These newly uncovered clusters are not just curiosities. They are keys to understanding how the Milky Way grew and evolved. Globular clusters are thought to be among the galaxy's first building blocks, remnants of the earliest star-forming epochs. Some may have arrived during ancient galactic mergers, while others may have formed in situ during the early collapse of the galactic halo. By studying their motion, composition, and structure, astronomers can reconstruct the early history of the Milky Way, star by star, cluster by cluster. Thanks to VISTA's unprecedented view, that history is finally coming into focus. While globular clusters are ancient, massive, and tightly bound, open star clusters are their younger, more delicate cousins. These clusters are formed from the same stellar nurseries that give birth to stars, but they are looser in structure and contain far fewer members. Typically made up of only a few hundred or a few thousand stars, open clusters are often short-lived on cosmic timescales. Over time, their stars drift apart due to gravitational forces. Yet, despite their youth and beauty, many open clusters remain hidden, too faint or too shrouded in dust to be seen with traditional telescopes. Thanks to the VISTA infrared survey, that is now changing. By peering deep into the dusty regions of the Milky Way, where visible light cannot reach, astronomers have uncovered a treasure trove of new open star clusters. At least 96 previously unknown open clusters have been identified, many of them tucked away near the central plane of the galaxy. These clusters had gone unnoticed for generations, lost in the noise of brighter, older stars, or obscured entirely by cosmic dust. With VISTA's help, we are finally beginning to see them in all their quiet glory. One of the most remarkable things about these clusters is how subtle they appear. Unlike globular clusters, which are compact and striking even from a distance, open clusters are spread out, often indistinguishable from the background unless viewed in the right light. VISTA's infrared vision allows astronomers to spot the slight overdensities of stars, subtle groupings that betray the presence of a cluster. It is like detecting the faint footprint of something that was once nearly invisible. The discovery of these clusters requires not just powerful technology, but patient, careful analysis. Among the newly discovered clusters is one particularly interesting example, VCL003. Located more than 15,000 light-years beyond the galactic center, it is one of the first open clusters ever observed on the far side of the Milky Way. That alone makes it significant. Because of the dense gas and dust between us and the far side of the galaxy, we have always struggled to map what lies beyond the center. Now, with discoveries like this, astronomers are beginning to sketch in the missing half of our galactic map. These open clusters are not just beautiful, they are scientifically valuable. Because they are young, their stars still carry the chemical signature of the gas clouds from which they formed. Studying their composition tells us about the environments where new stars are being born. Their distribution and movement also reveal how material flows through the galactic disk. And since some of these clusters are located in extreme or unexpected places, they offer clues about how far the processes of star formation reach and how interconnected the galaxy truly is. In the grand story of the Milky Way, open clusters are like punctuation marks, short bursts of creation that appear, glow, and eventually fade into the background. Yet without them, our understanding of stellar evolution would be incomplete. Thanks to VISTA, we are beginning to find them in places we never thought to look. These discoveries remind us that the galaxy is not a static structure, but a living, breathing ecosystem of stars in motion. Even in the quietest corners, even behind the darkest dust, something young and luminous is always waiting to be found. It is one thing to take a snapshot of the stars. It is another thing entirely to track how they move through space. That is the difference between seeing the galaxy and truly understanding it. The Gaia mission, led by the European Space Agency, was launched with a single purpose: to create the most accurate, dynamic three-dimensional map of our galaxy ever attempted. And instead of relying on brightness alone, Gaia does something extraordinary. It watches how stars shift, sway, and drift over time. In essence, Gaia does not just take pictures, it listens to the heartbeat of the Milky Way. The secret to Gaia's precision lies in a concept known as parallax. When observed from different points of view, nearby objects appear to shift against distant backgrounds. You can see this effect by holding up your finger and alternating which eye is open. That shift is parallax. Now imagine doing this from one side of Earth's orbit to the other, millions of kilometers apart. Gaia uses this orbital motion to detect minuscule changes in a star's position over time, allowing scientists to calculate its distance with unprecedented accuracy. But Gaia does not stop there. It observes each star not just once, but dozens of times over the course of its mission. As Earth moves, and as the stars themselves drift through the galaxy, Gaia tracks both position and motion, what astronomers call proper motion. Combined with brightness, temperature, and chemical composition, Gaia's data creates a complete profile for each star. Over the years, this mission has gathered over 1 billion such profiles, turning our galaxy into a dynamic map, alive with motion. What Gaia has uncovered is astonishing. Not only does it show where stars are, it shows where they are going and where they have come from. By running the data backward in time, astronomers can reconstruct past galactic events. By running it forward, they can predict future configurations. Gaia has revealed that many stars near us are not native to this region at all. They are visitors, remnants of ancient collisions or migrations. Some even move against the general flow of the Milky Way, hinting at a violent, cannibalistic past. This level of detail has never before been possible. In previous maps, stars were points of light frozen in time. Now, with Gaia, they are trajectories, histories, and futures. Gaia has allowed scientists to model the complex motions of stars within spiral arms, to detect subtle gravitational distortions, and even to infer the presence of unseen objects like dark matter or black holes. It is not just a static map, it is a living simulation of the galaxy's inner workings, built from real observations. And perhaps most importantly, Gaia's work complements the infrared revelations of VISTA. Where VISTA uncovers what is hidden behind dust, Gaia traces how everything moves together in space. One looks through the veil, the other maps its shifting structure. Together, they are revealing a galaxy that is not only more crowded and complex than we imagined, but also more alive. Thanks to Gaia, we are not only beginning to chart the geography of the Milky Way, we are starting to grasp its choreography, an intricate, celestial dance billions of years in the making. As Gaia mapped the Milky Way with unprecedented precision, it began to uncover something unexpected. Ghosts. Not literal ghosts, but stellar remnants of long-vanished galaxies that no longer exist in any recognizable form. Among the countless stars Gaia observed, a group stood out. These stars were moving in the wrong direction. While most stars orbit the galactic center in a similar direction, this group appeared to be swimming upstream. Their motion, brightness, and color all suggested they were not born in the Milky Way. They had come from somewhere else. Astronomers traced their motion and properties backward in time and discovered a remarkable story. Around 10 billion years ago, a smaller galaxy collided with the Milky Way. This ancient galaxy, now referred to as Gaia Enceladus, was swallowed by our own. Its stars were scattered, stretched, and absorbed into the structure of the Milky Way, leaving behind only a faint stellar trail. Gaia allowed scientists to identify over 30,000 of these stars, spread across the sky but united by their shared origin and trajectory. This event was not gentle. The collision between Gaia Enceladus and the young Milky Way likely shook the entire structure of our galaxy. It may have been responsible for heating and thickening the galactic disk. It may have even triggered the formation of the Milky Way's central bar, a feature not found in every spiral galaxy. The Milky Way we see today is, in part, the product of this cosmic accident, shaped by the absorption of another stellar system billions of years ago. But Gaia Enceladus is not alone. The Sagittarius dwarf galaxy, a small companion to the Milky Way, has already collided with us at least 3 times over the past 5 billion years, and may be on course for a 4th. Each time it passes through our disk, it loses stars, pulled away by our galaxy's gravity. Some scientists even suggest that one of these encounters may have triggered the formation of our own sun. Galactic collisions are not just ancient history. They are ongoing, shaping star formation, structure, and motion throughout the Milky Way. These acts of galactic cannibalism are more common than you might think. Dwarf galaxies orbiting larger ones are often torn apart over time. Gaia's data has revealed hints of several such past events in the Milky Way's halo and thick disk, each leaving behind its own stream of stars. Some of these streams are so faint and diffuse that they were invisible until Gaia's precise motion tracking exposed them. The outer regions of our galaxy are littered with these stellar fossils, each one a chapter in a very long and violent history. The discovery of Gaia Enceladus has changed our understanding of what the Milky Way is. It is not a pristine structure, grown in isolation. It is a composite, assembled over billions of years through collisions and mergers. Like cities built atop ancient ruins, the Milky Way's stars rest upon layers of forgotten galaxies. Thanks to Gaia, we can now peel back those layers, one by one. And what we are finding is that even our peaceful night sky hides a story of violence, chaos, and creation. A story written in the motion of the stars. While Gaia is best known for mapping stars, its precision and persistence have allowed it to reveal far more than just starlight. By watching the motions of objects across the sky over many years, Gaia has uncovered some of the most elusive and invisible phenomena in our cosmic neighborhood. Among its many unexpected discoveries are black holes without companions, tightly bound binary star systems, and even asteroids drifting silently through our solar system. Each of these findings opens a new chapter in our understanding of the universe and of the Milky Way itself. Let us begin with black holes. Most of the black holes we have detected in the Milky Way are discovered when they interact violently with nearby stars, pulling in matter and emitting intense X-rays. But what about the silent ones? The black holes that do not feed, do not shine, and do not scream. Gaia found one of them. By tracking the motion of a visible star, astronomers noticed that it was wobbling in a strange and subtle rhythm, as if being tugged by an invisible companion. That companion turned out to be a black hole, over 30 times the mass of our Sun, located just 2,000 light-years away. This discovery is significant for several reasons. First, it proves that there are likely many more black holes hiding quietly in the galaxy, invisible to traditional telescopes, but leaving behind gravitational footprints. Second, the sheer size of this particular black hole was surprising. Most local black holes are about 10 times the mass of the Sun. Finding one 3 times larger suggests that massive stellar collapse may be more common than we thought. And Gaia's precision tracking may be the key to finding more of these silent giants. Gaia has also transformed our understanding of binary stars, systems where 2 stars orbit around a common center of mass. While binary stars are not rare, identifying them can be tricky, especially when the stars are close together or when one outshines the other. Gaia's detailed motion data has revealed hundreds of thousands of binary systems, including many that were previously unknown. By tracking the subtle dance of these stars over time, Gaia is helping astronomers determine their masses, orbits, and even their evolutionary stages. But Gaia does not stop at distant stars. It also looks much closer to home. By observing the small shifts in light from moving objects, Gaia has tracked over 150,000 asteroids in our solar system. Some of these are known objects with well-defined paths, but others are newly discovered wanderers. Even more interesting, Gaia's data revealed that at least several hundred of these asteroids are not alone. Their motion indicates the presence of tiny moons, asteroids orbiting other asteroids. This nearly doubles the number of known binary asteroid systems. These discoveries, from monstrous black holes to fragile asteroid pairs, show just how versatile Gaia truly is. It is not just a telescope looking at stars. It is a dynamic observatory that captures the shifting mechanics of the cosmos at every scale. Each new object Gaia reveals, whether near or far, challenges what we think we know about space. And as more data is processed and released, there is little doubt that Gaia will continue to illuminate the invisible, uncovering the silent forces and hidden players shaping the galaxy we call home. as the Gaia mission begins to wind down, it leaves behind a legacy of precision, discovery, and transformation. But space science does not pause for long. Even before Gaia took its final measurements, astronomers and engineers were already looking to the next generation of telescopes, ones that would build upon Gaia's achievements and push even further into the unseen corners of the cosmos. Two names now stand at the frontier of this vision: Gaia, NIR, and Euclid. These are not just upgrades, they are evolutionary leaps in our effort to chart the structure and fate of the universe. Gaia NIR, short for Gaia Near Infrared, is envisioned as the spiritual successor to the original Gaia telescope. While Gaia focused on visible light, Gaia NIR will see in wavelengths that penetrate even deeper into the dusty mid-plane of the Milky Way. This shift is more than cosmetic, it is essential. Many regions of the galaxy remain hidden behind thick curtains of gas and dust that block visible light. By observing in the near infrared, Gaia NIR will be able to track stars, clusters, and structures that have remained out of reach until now. The timing of Gaia NIR is intentional. Set to launch approximately 2 decades after the original Gaia mission, it will allow astronomers to measure how far stars have moved during that interval. This longer baseline will sharpen parallax measurements, improve motion tracking, and reveal subtle gravitational interactions. In other words, Gaia NIR will not only map the galaxy, it will show how it has evolved over time. With better access to obscured regions and more accurate long-term data, the next Gaia will take 3-dimensional mapping to a level never before achieved. While Gaia NIR looks inward, the Euclid telescope is designed to look outward, deep into the vast reaches of the universe. Launched by the European Space Agency, Euclid's mission is nothing less than to unravel the nature of dark matter and dark energy. These two invisible forces make up the majority of the universe's content, yet they remain almost entirely mysterious. Euclid will study how galaxies cluster together, how their shapes are distorted by gravity, and how the universe has expanded over billions of years, all in an effort to understand what holds the cosmos together. What makes Euclid so powerful is its ability to gather both visible and near-infrared light across enormous regions of sky. Its ultra-wide field of view will allow it to capture light from billions of galaxies, some as far as 10 billion light-years away. This will produce the largest and most detailed 3-dimensional map of the large-scale structure of the universe ever made. Euclid will measure cosmic shear, gravitational lensing, and the geometry of space itself, all with the goal of detecting the subtle fingerprints of dark energy shaping the cosmos. Together, Gaia NIR and Euclid represent a dual mission, one looking deeply into our galactic home, the other far beyond its borders. As one maps the structure and motion of the Milky Way in exquisite detail, the other charts the cosmic web of galaxies stretching across the universe. It is a vision of astronomy that is no longer bound by the limitations of visible light. Instead, it embraces the full spectrum, the full scale, and the full mystery of the cosmos. And with these instruments, the next chapter of discovery is already beginning to unfold. The first images from the Euclid telescope arrived like whispers from the edge of time. Designed not to capture beauty, but to uncover truth, Euclid surprised even its creators with images more breathtaking than anyone expected. Galaxies crowd the frame in the thousands, each one a swirl of stars and dark matter, each one a window into the distant past. Some of these galaxies are so far away that their light began its journey toward us when the universe was still young, less than a quarter of its current age. But Euclid is not just taking pictures, it is tracing the invisible. Dark matter, the elusive substance that makes up most of the mass in the universe, cannot be seen directly. However, it bends light through gravity. As light from distant galaxies travels across the cosmos, it passes through dark matter, which subtly distorts the image. Euclid's instruments measure this distortion with incredible precision, allowing scientists to build a detailed map of where dark matter is, without ever seeing it. In one of its first deep-field images, Euclid captured the Perseus cluster, a massive gathering of galaxies hundreds of millions of light-years away. Behind the visible galaxies lie countless smaller, fainter ones, whose shapes have been gently stretched by unseen gravity. These slight warps in shape are Euclid's treasure, the signature of dark matter. With its wide view and infrared sensitivity, Euclid can detect not only the large, bright structures, but also the small, faint ones that are critical to understanding how dark matter works on different scales. As Euclid continues its mission, it will scan a third of the sky, creating the most detailed three-dimensional map of the large-scale structure of the universe ever made. This map will help us understand how galaxies cluster, how cosmic structures evolve, and how dark energy drives the expansion of space itself. Euclid is not just another space telescope. It is a cosmic cartographer, charting a universe shaped by forces we still barely understand. With every image, it brings us closer to revealing the hidden framework of reality. We used to think the Milky Way was something distant, a painted streak of stars across the sky. But now, we know better. It is not just a static backdrop. It is a living, breathing structure filled with motion, transformation, and mystery. Thanks to missions like VISTA, Gaia, and Euclid, we are beginning to see our galaxy not as a flat image, but as a complex, evolving system, where stars are born, die, drift, and collide. We have uncovered hidden clusters, revealed ghost galaxies, traced dark matter, and watched stars dance through space. Yet, we are still just at the beginning. With every new observation, the Milky Way becomes less familiar and more beautiful. This is not just a map, it is a revelation. And the more we look, the more alive our galaxy becomes. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.